Okay, in this lecture we start a very important concept, numerical analysis. We call it, in fact, interpolation. Before I start to interpolation and the methods and techniques for computing an interpolant, we need to know that what is interpolation. Let me start with a very simple example. Suppose that you have the population of a country in some different years, in fact, decade. For example, in 1950, we have this population for a country in thousands, in fact. In 1996, we have this one, and so on. If you plot these points on a coordinate system, you will get, for example, in 1950, this point, and the other one, the other one, the other one, the other one, and the other one. But if we want to know, for example, the population of this country in, for example, 1963, how much is it? Or, for example, we want to know in here, for example, 1997, how much is the population of the country? For this one, for finding this value, we need a new concept in numerical analysis. We call it interpolation. Okay? Now, let me start with a theorem we called Weierstrass approximation theorem. Let f be a continuous function on an interval a and b. Then, for all epsilon greater than 0, there is a polynomial of p of x, such that the absolute value of difference between f of x and p of x is less than epsilon for all x in the interval a and b. What does this theorem say? In fact, this theorem says if you have any function, any continuous function in an interval, then you can find a polynomial that approximates the function f of x at every point in the interval. This is the meaning of the Weierstrass approximation theorem. And we note that the bound is uniform. In fact, it means that it's valid for all x in the interval. And the other one, this theorem says nothing about how to find the polynomial. The theorem just says about the existence of a polynomial, that we can do something like this. For example, you suppose that you have something like this. A point here, point here, point here, point here, and for example, point here. Okay? Then we can, for example, find a polynomial like this. Okay, this is a, for example, interpolant polynomial. This is the, in fact, the concept of Weierstrass approximation theorem. But what we need is how to find this polynomial and how can we find it. This is the, in fact, geometrical illustration for the Weierstrass approximation. If you consider the blue curve as the exact curve of the f, then these two, in fact, red plots is f plus epsilon and f minus epsilon, and we can choose small epsilon. Then these two curve are going to fit on the blue one and in fact on the exact one. But our problem is that how can we find this polynomial? The natural question is that the Taylor polynomial is a good candidate for the interpolant polynomial. We say it's not true, and the Taylor polynomial is not enough good for this aim. In fact, Taylor polynomial maybe is good for some functions, but the Taylor expansion works hard to be accurate in the neighborhood of 1 point. Okay, and in some functions maybe it doesn't work good. Let me show you an example about the Taylor polynomial for e to power of x. E to power of x, exponential of x. We know that this curve, the blue one is the curve of exponential of x. If we consider the Taylor expansion for e of x to form sum n equal to 0 to infinity, in fact x to power of n over n factorial. If we consider n equal to 0, we have just p0, x equal to 1. This line, this is p0. If we consider p1, it will be 1 plus x, so it will be this line. If we consider n equal to 2, so it will be 1 plus x2 over 2. This is p2. For p3, we have a cubic polynomial, and the curve is this one. For p equal to 4, we have this polynomial, and this is the curve. For p5, we have this polynomial of degree 5, and this is the curve. And if we continue in the same way, you can see that when we increase the degree of the polynomial, the curve of the polynomial is going to be close and close and close to exponential of x, and in fact the Taylor expansion for e to power of x is okay as an interpolant. It's okay and there is no problem. But if, for example, you consider f of x equal to 1 over x, then the Taylor expansion about x equal to 0 is something like this. Pn of x equal to sum k from 0 to n minus 1 to power of k times x minus 1 to power of k. Okay? And if we consider f of 3, we know that f of 3 is 1 over 3, 1/3 in fact. But if we compute Pn of 3 by the Taylor expansion, we detect that for n equal to 0, Pn3 is 1. For n equal to 1, Pn3 is minus 1. For Pn equal to 2, it's 3. For n equal to 3 is minus 5, and so on. And you can see that Pn of 3 is not 1 over 3, and it's very, very, very far from 1/3 in fact. So the Taylor expansion doesn't work for this function, and this is the reason that we need other techniques for finding the interpolant polynomial in fact. Okay, so we need some other techniques. There are lots of techniques and methods for finding an interpolant. For example, Lagrange polynomial or Neville method. we have Newton divided difference, Hermite interpolation, cubic spline, and geometric spline, fractional, and lots of other techniques to finding the interpolant. Okay, so let me start with, before I start to Lagrange polynomial, let me start with a very easy and very in fact natural way to finding an interpolant. But before I start that, I should say that this is not good, and this is the worst method to finding an interpolant. First, let me explain the concept of interpolation and the definition of interpolation, and I in fact start with some notation and some concepts about the interpolation. We have n plus 1 points like x0, y0, x1, y1 to xn, yn. Okay, these points are called nodes. If we have some points like this, we call all of these points nodes. The y values are assumed to come from some underlying function f. It means yi equal to f of x0. For example, if you consider, for example, f of x equal to 1 over x, and you try to draw some table. You consider here y and x and y. Consider x equal to 1, y is 1 over 1, is 1. X equal to 2, it will be 1 over 2. 3, 1 over 3, 4, 1 over 4, and so on. This is, in fact, maybe a source of the nodes. Or also we can have an experiment and we get some results. For example, you calculate the temperature of something in, I don't know, everything you can consider. For example, a year, okay, and population. For example, in 1905 is 25,000. In 1916 is 207,000, and so on. Okay, every pair is a node here, and also here every pair is a node. Okay, now if you consider a figure like this, if you have some points here, this big blue circle are nodes. In fact, this is a node. We have, for example, 3 points here. If we can find a polynomial like p of x that pass through these nodal points, these true nodal points, then p of x, it is an interpolant. Okay, or for example, for these 3 points we can have something like this polynomial. Also, this can be an interpolant. So an interpolant is a polynomial of degree. For example, for 3 points it can be from degree 2. Okay, that pass through these points. Now, what's the mathematical definition of interpolation. We define the interpolating polynomial for the set of n plus 1 nodal points x0, y0, xn, yn as a unique polynomial of p in Pn. When we say Pn, in fact, Pn is something like this. When we say Pn is the set of all polynomials of degree at most n. This is in fact an xn to a0 such that an is not equal to 0. This is the family of the polynomial of degree n. Okay. Now, when we say the interpolating polynomial of n plus 1 nodal point is a polynomial belong to Pn such that p of xi is exactly equal to yi for all I equal to 0, 1, 2, n. This is the mathematical definition of the interpolation, and our aim is to find some polynomial like p that interpolate the nodal points. Okay, now we have different kind of, in fact, interpolant. Let me start with the simplest, in fact, method and the most natural technique in the next lecture, and stop here. Please follow my channel and introduce my channel to your friends. Thank you.